Okay, why I went to this, I don't know, because I'm going to start with a video. My wife showed this to me, and I thought it was good enough to share with the class. We've been talking about relativity, and one of the very, very basic precepts of relativity is nothing can go faster than the speed of light, right? So, how fast does light travel? 3 times 10 to the 8 meters per second. I was right in precise. 2,997,92458 meters per second. Okay, so can we watch light travel?
I do it all the time.
But what you cannot do, you do. At the beginning of this video, I was thinking that. I was like, well, of course we can take pictures of light. That's what our pictures are, is taking pictures of light. But we can't actually observe its motion because it's going way too fast for us to see it. It would all streak together. Something we didn't talk about is the framing rate of our eyeballs. Our eyeballs essentially take movie pictures. And movie pictures, you have so many frames per minute or per second. And our eyes take, what is it? A picture about every, okay, now I think it's about 20 pictures per second. Is about the rate at which our eyes take a picture. And so if you calculate how far does light travel in 1/20th of a second, well, it'd be 3 times 10 to the 8 divided by 20, which is about 1.5 times 10 to the 7 meters. So 17 million meters. You can't just watch light travel 17 million meters between one frame and the next frame. So we can't watch it. Now, the slow-mo guys, they have some really awesome cameras with very high frame rates so they can watch things happen that occur very quickly. And for this episode, they went to Caltech, and Caltech has developed a camera with higher frame rates. 10 trillion frames per second is their highest frame rate camera. 10 trillion, what is 10 trillion? 1 followed by how many zeros? 10 to the what power?
Maybe 12.
Okay, a million would have been 6.
Yeah.
Billion would be 9. Trillion is 12. So since it's 10 trillion, it's 10 to the 13. Well, if you're taking 10 to the one picture every 10 to the 13th of a second, light is moving less than a millimeter between frames. So with a camera that fast, you could actually easily watch the progression of light. And so that's what we're looking at in this video. With apparently no sound. There we go.
All right, here we go.
So this
What
is...
we're seeing here is the balls that's been comped in, basically. Yeah, so this camera only detects the light itself.
Okay. The camera just detected this blue you're seeing, and then the guy just took a picture with his iPhone and superimposed the bottle with the milky substance that it was going through. So you have the light hitting the milky substance and then scattering so that you could see where the light was as it went through. You don't see the light before the bottle because it was traveling through air and you didn't have significant scattering.
Which is a bluish laser light, which is why you don't really see anything else other than the light looking like that.
This is a very high power femtosecond laser.
In the room with my actual eye, it looked like it was constantly lit up, but here we're able to follow the...
What was your question?
So why'd they keep the label on? The light kind of just disappeared.
They didn't keep the label on. They put a piece of paper on that says Caltech because this was done at Caltech.
Oh, they're advertising.
That's advertising.
You should have put it along the side.
Yeah.
light moving through the bottle. It may not look like it, but this is actually real. It's refracting the photons, that's why you can see it. But when it's just going through the air, there's nothing to actually reflect the light. Yeah, it's only showing up in the bottle. It is interesting. It almost looks like a sort of an 80s film effect. It does, doesn't it? It looks like some sort of ghost flying into the room, but actually that is light.
I just noticed something I didn't notice the first time.
10 picoseconds.
Look at Dan's lab
We're
jacket.
just casually watching this light go left to right through the bottle, but in reality, the light is moving a million times faster than a bullet. Mental subject. Yeah. Okay, so we've shot light through milk. Next experiment? Yep. All right.
Well, did you notice his lab coat?
cavity.
It's all ripped up. Okay.
So when light comes
So we're not going to look at the technology. Okay, well, actually, yeah.
Call it chaotic cavity.
They're going to have light bounce around in this little cavity. So you see that shape?
Times by the mirrors surrounding in the cavity.
So they're going to take pictures of the light bouncing around that cavity. And here's video of the light bouncing around the cavity.
Pulse of light bouncing around.
Is that cool? It just looks like a BB bouncing around, of course.
And this is 1 femtosecond of laser pulse. So as if you just went like with the laser, a femtosecond pulse. Yeah. And if you pause it, you can see it's like a dot of light. And if look,
what's a femtosecond?
A very small second.
What does femto mean? It's one of those prefixes.
Femto?
Femto. F-E-M-P-T-O.
So then just the opposite, isn't it 1 times 10 to the negative 9?
It's minus 15.
Oh.
You go, of course, milli 3, micro 6, nano 9, pico 12, femto 15. So this is a pulse that's 10 to the minus 15 seconds long. When I was in graduate school, some of my classmates were working on developing the first femtosecond lasers. It's a technology that was not around when I was your level.
like comped in the shape of the mirror. Yeah. I wonder if you could actually build like a big maze to get it around. Like you could do like a little maze.
Okay, enough of that.
The world's fastest.
Go on to. Okay, this here.
Now I'm doing 500 billion per second.
It's a faster camera, and they're watching the camera sweep across
Casual half trill.
these little statuettes they made of themselves.
This is 500 billion frames a second of our little figurines with a resolution of 549 by 439. The footage is played back at 20 frames a second, therefore it is slowed down by a factor of 25 billion times. I do like that I was able to successfully photobomb this picture.
Okay.
I like how it shows
Now the last
nose.
thing that is the
Oh,
coolest
amazing.
thing. This is the one that it's a different camera that takes the 10 trillion frames per second. And actually, yeah, it's right here.
The lights seem to be going the same speed, but then you've got to remember that the scale of this is much smaller. So this is 1 millimeter, it says here.
So you can see, yeah,
before an entire bottle.
they're able to take
Which shows you
pictures
that
with
we
that
actually
kind of
call light
resolution
traveling through such
in
a small
time.
amount of space. And it's so slow now that our picosecond has a decimal place to the 100th femtosecond. That's blowing my mind for a start.
Now, after we watched this, my dear wife said, "What's the point?" And that's not a dumb question. What is the point?
Get a better understanding of the nature of life.
I think there is some of that, but in my thinking, it's more how it can be applied to things like chemistry. Because you have chemical reactions, and those reactions occur very quickly. And you have things like, well, one of the things I read about, a decade or more ago, was about the bonds between oxygen and hydrogen and a water molecule and how they actually shift up in time. That it's not just a static thing. Or how you have resonance bonds. You guys know about like benzene rings, right? The resonance. And you can actually watch to some degree what's happening there. Now, probing the bonds is a difficult thing to do in itself, but that's a reason to develop high speed so you can get a better understanding of what's really going on because it happens so fast. Why did I show this today? Because that speed of light issue is very relevant to what we're doing. I left the title as addition of velocity because I didn't notice it and I just went on to the other things. Now we're going to talk about today, our goal is to understand how relativity affects other things in physics besides just the work in the space-time continuum. So we have a number of different things, and one of them is the Doppler effect. Now, I don't think first semester we actually carefully talked about Doppler shift, did we? Or correct me if I did.
We covered it.
Okay, we did cover it a little. Okay, so the Doppler shift is the effect with sound. If something's coming toward you, the frequency is shifted to a higher frequency because the waves are being received by you the one that was, well, they are actually compressed in space. If the object is moving towards you, the wave fronts from, second wave and third wave are closer to you when they start. So the wavelength is physically smaller. And so something's coming toward you, you hear, and then when it passes you, it goes to a lower frequency as it passes. You have the same type of thing occurring with the Doppler shift, but it's different. It's different because our sound was traveling in air, and if the air is traveling at different speed, your sound is going to travel differently as well. So the sound speed is relative to air. Light, its speed is not relative to anything. It's the same in all reference frames. So a moving source is going to actually behave differently. And so what I have here is just the comparison between the two equations. This is for sound, as is clear by the subscript sound. And this is for light or electromagnetic waves. So you see, those are not the same equation. What's the difference? Well, a square root for starters. You have a square root in one and not the other. Instead of speed of sound, you have speed of light, so that's the same. And then you had speed of the object on top instead of speed of the observer, and minus the speed of the object on bottom instead of the speed of the source. So there are some significant differences, but you still have a Doppler effect. So you still have, if something is coming toward you, let us say it's a star, and that star is coming toward you, you are still going to see a shift that's going to shift to higher frequencies. And so we call that a blue shift because blue is on the high frequency side of the visible spectrum. If a star is moving away from you, you see it shifted toward the low frequency edge of the spectrum, which is red. So we call that a red shift. And so in astronomy, this Doppler shift is used extensively to determine how fast things are moving toward and away from us. And then using the work of Hubble, that's used to determine how far away from us they are. So that's the equation. Simple thing for you. I would only ask you a conceptual question about this. I wouldn't ask you to do a calculation. So a conceptual question would be, if something is moving toward you, how is the frequency shifted? What's the answer? To a higher frequency. If it's moving away from you, it's shifted to a lower frequency. Something a lot of people don't realize. In fact, I had a colleague physics teacher who talked to me and said, did you know that there's a Doppler shift if it's not moving away from you or toward you for light? Yes, there is. If something's going around you at constant speed, there is no Doppler shift for sound because it's not getting closer or farther. But with relativity, there is, because if it's moving around you in a circle, what is different between your observation and theirs? Well, they are accelerating, yes. I'm talking about what we've studied in the last 2 days. What's different? Or 2 lecture periods. The time is passing at a different rate. So is distance, because they're in a different reference frame. But we're going to focus on the time. Because their time is passing at a different rate, the frequency they're emitting is not going to be the frequency you receive because of that time dilation. So that's why you have a Doppler shift even if something is moving tangentially, not coming closer or away. So that's a difference between the relativistic Doppler shift and the sound Doppler shift. You have a relativistic Doppler shift even if something's doing a circle around you. Momentum. This is something we're going to spend more time on that you definitely will have problems on. So momentum, we have a new equation for momentum. The old equation is not valid. So momentum is now gamma m, and then what does U stand for? Okay, U is the speed of the object. I was surprised that DJ answered. I expected one of the 4 people in physics 252 to answer because that's where I defined it, I think. He's faster. So U here and gamma, notice gamma is based on U. The speed of the object with respect to U. So we're reserving V for speed of a reference frame, U is the speed of an object in your reference frame. But gamma is the gamma for that object. So the first question to ask is, does that mean that what we learned before, okay, I know you all know this. What we learned before was momentum is mass times velocity. Or we could say m times u using the nomenclature here. And now I said that's not valid. How do these two equations relate? What's the difference in the relativistic momentum and the non-relativistic momentum?
The lack or presence of the gamma.
The lack or presence of a gamma. They're still both vectors, right? Still a vector. But you have a gamma in the relativistic and you don't in the one we've learned. And now I just told you the one we've learned is wrong. And if I was you, I would be just a little peeved because I spent a lot of time learning about momentum. And so you're like, why did you teach me wrong before you taught me right? And by the way, we're not going through, well, actually, I think I will have a little derivation for this, but it requires calculus, so a little hand waving there. Why did I teach you wrong before I taught you right? Go ahead, Mary.
Well, what if the old momentum equation work? Like, we're not moving fast enough that needing to make it relativistic, it doesn't matter at that.
That's exactly the key. If you have something that's moving at, let's say, 5,000 meters per second, 5 times 10 to the 6 meters per second, gamma is still approximately 1, right? It's 1.00 something. So what's the difference? It's still perfectly valid at that extreme speed. It's only when you're getting up to like 10% of the speed of light or faster that the two diverge. So that's why I taught you, quote, wrong originally, because it's perfectly valid for any situation that we're likely to encounter. So that's our equation for momentum now, a different equation. Force. You know Newton's second law? This is not it. I told you before that that was correct if the mass was constant. If the mass is constant and you're non-relativistic. If you're relativistic, that's not it. Newton's second law is truly stated in the way I have shown up above. This is actually Newton's second law, and this one is correct. Because we had two postulates of relativity. And like I said, I'm not sure which order I gave them to you, but one was that the speed of light in vacuum is a constant in every inertial reference frame. The second one is that the laws of physics that we learn work the same in every inertial reference frame. And so we still need to have Newton's second law because that's one of the laws of physics we learned. But that's the form that's correct. The other form was an approximation that doesn't work in relativity. So the net force, sum of the force vectors, is equal to the change in momentum over change in time, or to be absolutely correct, the derivative of momentum with respect to time. That's the correct equation for Newton's second law. And so that's going to have some important ramifications. So let's take a situation here. A cosmic ray collides with atoms or molecules in the upper atmosphere. Well, we talked about that Wednesday. But now we're going to be specific. We have a proton moving at 0.70 C, makes a head-on collision with a nitrogen atom initially at rest, and recoils at 0.63 C. What's the speed of the nitrogen atom after the collision? And it says we can just use 14 and 1 for our masses. First question, we talked about conservation of momentum. What condition was necessary for momentum to be conserved?
Had to be conservative. Like, there couldn't be any non-conservative forces going out.
Okay, it's a little different.
Is it completely elastic?
That was for the
Is it completely elastic?
completely elastic actually goes with what DJ said.
Does it work? No, that's an issue too.
It was that the net external force had to be zero. The only forces acting would be internal forces. So internal forces, since our system here is the proton and the nitrogen, forces between those two, that's fine. But if there's external forces, like if there was gravity from the Earth, that would break it. Our problem doesn't specify anything else, so we assume that these are in isolation. If they're in isolation, then there's no external forces. Momentum will be then conserved. So we have the net external forces are zero, momentum is conserved. You always have to start with that before you do a conservation of momentum problem. Because if it's not conserved, you have no reason, it's not a fundamental rule of physics that momentum is conserved. It's if the net external force is zero. So we did establish momentum is conserved because the sum of the forces external equals zero. So if momentum is conserved, I simply have to calculate momentum initial equals and momentum final equals. So what was my initial momentum? Okay, we have to find gamma. That's right. So let's say gamma 1 is equal to square root 1 over 1 minus 0.70 quantity squared. I know I put the square root different than I have before, but square root of 1 over something is the same as 1 over the square root of something. 0.7 squared is 0.49. 1 minus 0.49 is 0.51. Square root of 0.51 is going to be very close to 0.7 again. So this is close to 1 over 0.7, but that's not the exact value. And I trust my friend Trace is going to tell me the correct value.
0.71.
So that was close. So it's going to be gamma 1 times the mass of the proton times U1, where U1 was equal to 0.70 C. What about what about the momentum final?
Same thing with the different speed.
Okay, so same thing with the different speed.
Gamma 2 is 0.776.
Okay, but there's another piece for gamma final, or for momentum final. What's that second piece? Plus gamma for the nitrogen, mass of the nitrogen, U of the nitrogen. So this is harder than it was before. It's harder than it was before. I can get numbers for the momentum initial, and I can get a number for the blue part of the momentum final, but then it's going to be a little harder. So let's get those numbers. So we're just putting 1 atomic mass unit for the proton, and we're using plus for going to the right, so that's plus 0.70 C. So 0.7 times 0.71 is, well, it's got to be really close to 0.49, right? But
Not what I got.
what did you get?
I got 1.49.
Okay, I've got to check it.
Yeah.
I don't know why I pulled out my iPhone to do math. I mean, it has a calculator, but yeah, it's 0.497.
Okay.
You probably used the number from the second one instead of the first one.
Yeah.
And then UC. I left it in terms of the speed of light. The blue one is going to be 0.776 times 1U times minus 0.63 C. minus because it was rebounding, going the opposite direction. So that's equal to minus 0.489 UC. So using our conservation of momentum, that's not a gamma, that's a mu. (0.497 plus 0.489) gives me Now, what did positive represent? Positive for my velocity?
It was the direction.
Going to the right, going the initial direction. So the fact that this is positive tells us the direction. So I'm going to erase the vector sign and say UN to right. So I did, yeah. By my picture there, I'm matching my picture. And notice it called it VN here, different books, different symbols. So now what I have to find is find the speed. Or did it say to find the momentum?
Speed.
Yeah, so to find the speed is going to take a little more work, right? So let's insert a page and continue. Page manipulation, insert one page. No, one page will do it. So what I have is 0.986 is equal to gamma nitrogen, mass nitrogen, U nitrogen. Let's divide both sides by M nitrogen. What is the mass of the nitrogen? 14. And there were units here. That was U times C, U. And so I'm going to end up with 0.0704 equals gamma n UN. And now I'm going to expand gamma. So that's what I have on the right side when I combine the two. Notice UN outside the square root is UN squared inside. So that's why it's squared. And then this simplifies to wait a minute. That's the most I can simplify this. So to solve for UN, I need to square both sides. And this is now units of just C. as you might have guessed, there's a quicker way of doing this. And so last of all, you calculate this, that squared, and then I need to invert it, which I'm sure this calculator can do. I just have to find out where it is. I think it's this one. And add 1, which makes virtually no difference. Square root both sides. C divided by clear, clear, clear. That was hitting a button by accident. So 0.0702 C, or we actually only had 2 sig figs, so 0.070 C. So that's how fast the nitrogen rebounds. That was a lot of work, and like I said, there is a quicker way of doing it. We just haven't gotten to that yet. But we can do conservation momentum problems. Which statement is untrue? 2 of these are correct, 1's incorrect. Which statement is untrue here? Okay, that was the important thing. Important outcome, momentum has a different equation. Momentum is gamma mv, not just mv. Energy has also a new equation. Now, Einstein proposed E0 equals mc squared. You always see E equals mc squared, right? It should be E0 is equal to mc squared. What that means, though, is important. What that means is mass is a form of energy. So this mass has 1 kilogram. That means this has a rest energy. If it's stationary, no gravitational potential energy, no anything, it still has a mass potential energy, we call it a rest energy, of 1 kilogram times 3 to the 8 squared, which is 9 times 10 to the 16. So it has an energy of 9 times 10 to the 16 joules. That's a huge amount of energy, right? So this has a lot of energy. Now, we like to take that and extrapolate to humans. I'm not fat, I'm just full of energy, right? Because my mass is a form of energy. Now, if you think about it, my mass really is a form of energy that my body uses. But it's using it as chemical energy. There is a higher, well, the bond strengths are smaller in the fat molecules than they are when it is broken down and it forms new bonds that are stronger bonds. And it releases the excess energy, and that's what my body operates on. So I do have more energy. We go into some crazy situation where we have to survive for 60 days on water. I am more fit for this because I have more energy. But we can't tap into that energy. But that's what Einstein said, is that mass is just a form of energy. So oftentimes, like in chemistry class, they say conservation of mass, one of our fundamental rules. That's not a fundamental rule. It's completely false. Mass is not conserved. Energy is conserved. And mass is just a form of energy, and you can shift from mass into energy. That's what's going on in an atomic bomb, is you're shifting from mass to energy. That's why we get energy from the sun. It's shifting mass into energy. So, units. Remember when I went back there and I read the mass of the electron and the mass of the muon question?
Sorry, this relates to the previous line.
Uh-huh.
So I guess as a future teacher, I just kind of want to know when we get to the sections like, stoichiometry and going through like different chemical equations and how they bring up the law of conservation of mass. So should that not be taught? Or
That-
'cause
that's-
I don't want to like.
that's a good
evolve,
question.
So,
If you're teaching a grade school student, I would never mention.
yeah,
That
because
it's not
imagine
right.
trying to like explain.
If you're doing a high school student, I would probably say that technically, according to Einstein, E equals mc squared, and so you can change mass into energy, so mass is not technically conserved, but for all practical purposes, if we're not making a nuclear bomb, it's conserved. I'd say something like that. Yes, DJ.
If energy is being put into our atmosphere, energy is leaving our atmosphere,
Mhm.
how is it conserved?
Energy being conserved is not saying the energy on Earth. It's energy in the universe. And so the energy of the Earth, I mean, we believe that the Earth is getting warmer right now, right?
Yes.
That means that we are growing in the energy of the Earth.
Yes.
We have more coming in than we're emitting. That's not a violation, because that's just this part.
So the whole universe as a whole has a set amount of energy.
Yeah.
Okay.
Until you get to astronomy and you learn about dark matter and dark energy.
Okay.
And dark energy is, there's apparently an increase in energy that's occurring. And we don't know why. So we call it dark energy. We don't know why
Increase
any.
or the source of the increase is dark energy.
Yeah.
Which one?
Well, we don't know what's happening.
Okay.
We know that the universe, everything appears to say that the universe is expanding and the energy of the expansion is increasing. And we have no answer for why. But Emmy Nether, she was a mathematician, she showed mathematically a proof that says energy has to be conserved. She has a mathematical proof for it, and so we believe it truly is true. And that leaves us really baffled about why we appear to have more and more kinetic energy in our universe.
What's the dark?
Yes. Dark means we don't know what it is.
Yeah, like dark matter.
Yep. Okay, units. When I went back there to talk about the muon, I gave its energy in giga electron volts divided by c squared, which is a really odd unit for energy, or for mass, excuse me. But when we're doing nuclear physics, we very often talk about energy as electron volts. We learned about electron volts before exam 1. The electron volt is the charge of an electron, 1.602 times 10 to the minus 19 coulombs, multiplied by 1 volt, which is 1 joule per coulomb. So it turns out an electron volt is just 1.602 times 10 to the minus 19 joules. So if we talk about energy in electron volts using E equals mc squared, then that gives me m is equal to E0 over c squared. And so when we list the mass of the electron up there, the energy, the rest energy of the electron is calculated to be 511 kiloelectron volts. And so its rest mass is 511 kiloelectron volts divided by c squared. We use that unit because it doesn't require us to do any thinking. I just take the number for its rest energy divided by c squared, and I have the answer. So you'll have this as a unit for mass in electron volts over c squared. And momentum, how does momentum relate to mass in terms of units?
It would be P over gamma U.
Okay, so gamma has no units. So in terms of units, momentum is units of mass times units of speed. Well, what do we have for the unit of speed in our mass equation? Speed of light. So momentum, we're just going to multiply by speed of light. And a unit for momentum that we will use is EV over C. It's a convenient unit for momentum. And of course, for energy, EV. So what I just said, this is just what I just said. There's nothing new to add there. Let's do a problem. What is the momentum of an electron moving at a speed of 0.80 c in units of kiloelectron volts per c? Do that, everybody. All right. No, okay. For those who don't remember, I will write the momentum equation.
Yeah.
Or if you prefer, gamma mv. And we're not doing vector, we're just doing the scalar.
If it's minus, then I did it. It's not.
I just hear this sound. It sounds like what is like an NES game and she's jumping. Every time she hits the calculator.
That's my phone.
I know, I'm saying a different sound. I have selective hearing and I choose a backwards. Okay. I have.
I have to do 11 also, but not cool. I was like, I don't know.
So we have the same number of 6.
There you go. I'm just wondering, like, yeah, square root is
What about the squares?
it's the gamma, right? Oh, wait. It pretty much got that answer.
You get it.
2.5 times 10 to 11. Alright.
So you got a 0.5 and I got a 0.3.
I don't know.
I didn't know if you did. How'd you do it?
I mean, I know what I did, but I don't know.
I didn't say you were.
It's like, geez, DJ, the pressure, man.
I'm just questioning the validity of your statement.
You're probably correct. I probably put something over there about.
1.679 times 10.
That's the case in your put it on.
No, 1.66.
It's the trouble.
Did you get one?
Yeah.
Oh, sure. This is
Oh, you put it in crazy units. You use C.
I
I don't know what it is in C. That's really it.
But if I multiply, but if I
Or actually, no,
multiply
C.
But if I multiply
Okay, I don't know
C,
what I did
or
there.
the value of C is 2.9, which I did the calculator. Isn't that in units per second?
You might have done it correct, but I have in units of keV per C.
Oh, okay, because I was like,
I didn't convert. I didn't keep it in C.
Okay, I saw a number of people who had it right, a few that had it wrong. So what we have to do is just break it down to pieces. We have to calculate gamma, and then we multiply them together. So gamma is defined as 1 over the square root 1 minus v squared over c squared. And this is the gamma I've been using all along to make life easy. 0.80 squared is 0.64.
I'm just kidding. You did do
And 1 minus 0.64 is 0.36. And the square root of 0.36 is 0.6. So gamma is 1 over 0.6. And so then we just have P is equal to 1 over 0.6 times my mass, which was given right here, 511 kiloelectron volts per c squared. And then I have my speed, which was given right there, 0.80 c. And so when you multiply that through, it's 4/3 times 511 kiloelectron volts per c. Notice I had a cancel between this c and one of those two c's. Or if you multiply it through, that gives us 681 kiloelectron volts per c. Okay? Any questions you want to ask about that?
Yeah, I accidentally times it by the speed of light instead of 0.80. So
Well,
yeah.
that would just give you different units.
Yeah.
So it's not the biggest mistake that ever happens, right? Michael?
The square root is actually the denominator.
It would be exactly the same thing if I had the square root like this. It means the same thing. Okay. This is, since we're only 3 minutes, the last problem I'm going to do today, but it's a really important one. Here is a nuclear reaction. It's the decay of carbon-14. Carbon-14 decays into a nitrogen atom and an electron, and I'll put L here. I'm going to follow the new nomenclature. All of my life, that's been a new subscript E with a bar over it. The bar over it means it's the antimatter particle. The nu means it's a neutrino. And the E meant electron. But actually, the truth is, for the last 20 years, it shouldn't have been called the electron neutrino. It should be called the light neutrino. So there's now light, medium, and heavy instead of electron, mu, and tau. So that's our process. Now, what you know about the neutrino is nothing at this point, right? Which is fine. The neutrino was predicted and then later discovered because they saw that energy wasn't perfectly conserved. We're going to calculate the energy for this without the neutrino. And what they found is energy wasn't perfectly conserved. They said either we were wrong about this fundamental thing or there's something else we're missing. And they said that something else we're missing would have to be smaller. We would have found it. And it has to have no charge because we can find things with charge fairly easily. So they said it's neutral and small, so they named it a neutrino because that's a diminutive suffix for, the eno is diminutive and the for neutral. So the neutrino has a very low mass and no charge. That's why we're ignoring it. So now if we look at this, we're going to compare the energy before and after. So the energy before, the rest energy, is mc squared. So before initial is equal to the mass of the carbon. Well, remember, it's mc squared, so the mass of the carbon is 3.999950 U, and then I need to multiply it by c squared. And at this point, we once again want to do things as easily as possible. So we have a conversion factor that's shown that says 1 atomic mass unit, 1 U, is 931.48 MeV per c squared. You can go ahead and calculate it just using, 1 atomic mass unit is 1.6 times 10 to the minus 27 and go through and do it. You need to use more than 3 significant digits. And so this is the same as 13.999950 times 931.48 MeV per c squared. And then we have times c squared. Why do we use the conversion factor? Because now the c squareds cancel. And so I just multiply those two together. And so what's the energy of the carbon atom initially? I'm just going to rely on trace. But I need you to give me at least 5 digits. Actually, let's go bigger than 5 digits just to make sure.
Okay, well, it's 13,047.6734.
Okay, that we'll go with that.
I mean, that's where it ends.
That's where your calculator stopped. Okay, so that's the energy we had before.
There's a 0 between 3 and 4.
Oh, yeah.
Yeah.
No.
No.
It's 13,000.
So there's 0 right there.
Like that?
Yeah.
Okay, now the after. Now for the final, notice we have a nitrogen with an electron missing and an additional electron. If we combine these into one thing, it's going to have the same mass as a nitrogen that doesn't have an electron missing. Now I said that is an electron. So I can just do that as the mass of the nitrogen, 13.999234, and then I'm going to use that 931.48 again, MeV per c squared times c squared. What does that give me?
13,040.00649.
So what we have is a very slight difference in energy. What gives? Right, we had 7.7 roughly MeV that we lost. Where does that energy go? Goes into primarily kinetic energy of this. And so that energy was released in the form of kinetic energy. Okay, we got to quit today. That's the fundamental principle of what's going on with nuclear fusion, though. Same idea. So we're going to do a lot more calculations on that in future chapters. But we have to have it now for the E equals mc squared equation.